everyone. Oh, can you hear me? Can you hear me at the back? Cool. How's everyone doing at 5 p.m.? Everyone still alive? Yay! I hope you enjoyed the whole day of talks. Thanks for sticking around until the end. So I'm Kat, or this weird Polish-sounding Twitter handle on Twitter. I live in London. I work for Monzo Bank, so some of you might know it from the flashy hot coral cards. And today I'm going to talk to you about performance optimization. So as developers, when we pick up a task, we usually like to start with planning. And you might do the proper planning with sticky notes on the wall, or you might just figure out in your head what you're going to do. And then you go off and do some coding, and then hopefully you write some tests with the code, or test first, whatever you prefer. And then the tests pass, great, deploy to staging, everything looks fine. We're good to go to production, right? Well, have we considered performance anywhere in this? And I think it's a very typical scenario. I don't really want to blame anyone for this, because let's just say it out loud. Analyzing performance is hard, and especially when you've never done it before, when you're facing it for the first time, and you have no idea how to get started. So I thought I'll try and show you today how you might go about starting with performance optimization, basically based on my own experience from having to do it the first time around and having no clue where to start. So first things first, let's remind ourselves why we should care about performance. I'm not going to spend too much time on this, because hopefully the answers are obvious to everyone. In case they are not, how about this? Fast is generally better than slow. Duh. Everyone wants fast. Memory efficient is good. Saving money by using less servers for running your application is good. Smaller AWS bill. Running out of memory in production is bad. And then suddenly, running out of memory in production is really bad. And then the language and the hardware improvements will only take you so far. In the PHP JIT RFC, there was a sentence that was saying that, from the PHP authors, that we believe we have hit the limits of op-cache optimizations. So essentially, up until round about 2004, performance was improving about 50% year on year. So that's the classic Moore's law. So all we had to do is just wait a bit until we got the latest hardware, and it just magically made things faster. And then we hit the limit of how much we can solve with just hardware. And so the rate of improvement these days is more like 22% per year. So you can see it in the top right. As Gordon Moore said, all exponentials come to an end. So gone are the days when we can just be lazy and wait for the hardware manufacturers to do our work for us. I'm not saying it's not improving. It is still improving. And then especially if you go into multi-core architectures, so instead of using one core for your application, you use all four at the same time. So if you have a concurrent design, you can still gain some improvements there. And I think this is why languages which promote concurrency are so popular these days, like Golang or all the other ones. And even in PHP, there are now frameworks popping up for doing concurrent programming. So Swool is one of the most popular ones these days. So that means that the ball is in our court again, in the developer's court. So that covers the whys in terms of when you should think about performance. Pretty much at every stage of the development lifecycle. So in development, when you're writing an app or when you're maybe asked to analyze an existing application, you should do it locally. It's very convenient because you can use any tools you like without worrying about affecting production. You might have a dedicated load testing phase before you release. You might have automated load tests running as part of your CI pipeline. And then even after you're done working on your software, pretty much after every deploy, you should still keep an eye on performance and see if you've made things better or worse. How is the app still doing? So you should monitor your application over time on production to spot any issues. So now we know the whys and the whens in terms of what should we optimize. Well, most of you probably have a pretty good idea already. We generally like to measure things like execution time and memory usage. Those are the two main things. It's good to establish the minimum, the maximum, and the average values for those. And this is very useful in itself. Like, performance aside, your sysads and your DevOps will love you for that information, because when you come to them for the first time and you go, hello, I would like you to deploy my application to production, please. And they ask you, well, what kind of server do you want? And you go, I don't know. So it's very useful to know what your application typically needs to operate. You could look into concurrency in PHP. So like I mentioned before, Swool is one of the frameworks. There is also React PHP. There is AMP. There is the pthreads extension, which has been around forever. And you could, of course, upgrade your hardware to the latest technology. It's also known as throwing money at the problem until you can do it, or until you can no longer do it, because you run out of options eventually. Sometimes it's genuinely the valid thing to do, so it's not always a bad thing. Like, sometimes you might have gained users over time, the traffic might have naturally increased. So sometimes it's a very, very valid thing to do, but more often than not, it's just running away from tackling the real problem, until one day you just have no other options and you have to face the real thing. So this is my very unscientific graph to try and illustrate the goal of optimizing performance. So we have three aspects. We have memory, time, and code. And so obviously we're aiming for that 0 point. We're aiming for using as little memory as we can, having as little code, so just the essential code to run our application, no dead code, no redundancy, and short execution time. But there is a bit of a caveat to this goal, because that 0 point is a little bit of a unicorn. Let's not forget that optimizing performance will often compromise the readability and the maintainability of your application. Sometimes you might come up with a crazy solution that, yeah, it's faster, but 6 months down the line, even you won't remember why did you do things in this really weird way. And you remember that it made things faster, but it's now not really easily understandable by you or your coworkers. So let's not forget that aspect and that potential danger. So I would say optimizing performance is just more of a balancing act. And you should really just stop at a sensible point. Like, don't desperately try to get to that unicorn. And make your app good enough for production, but also readable and maintainable. So for most people, their adventure with performance starts when their memory graph might start looking like the one at the top. So here you see the memory usage over time, and you can see that it's creeping up. And that seesaw-like shape, where the memory drops and then picks up again and drops and picks up again, that's just the garbage collection happening in the background. So it's a garbage collector doing its job, cleaning up all the unused objects and elements from memory so that it can be used again. So you can see that despite that still happening in the background, the overall memory used keeps creeping over time, which would suggest that there is a memory leak somewhere, and we can't free all the memory that we would like to be freed. Or maybe your graph looks like something like this. And that shows the request times. And you can see that generally everything's fine, except for those spikes. And one of them shows a 30-second request time. It's probably hit a timeout and then just got killed. And you might be wondering why, what your application was doing, what was it waiting on. Or maybe you got everyone's favorite, the dreaded PHP fatal error, memory exhausted, woo, black screen of doom or white screen of doom. So those are all clear signs of performance issues. Other than memory leaks, here are some other things that you might encounter. So you might have timeouts. So that's just your application being stuck waiting on something. If you are using concurrency in your design, then you have all the lovely stuff that comes with it, like race conditions and deadlocks and live logs. And then you might have just the everyday redundancy or inefficiency in your code. Maybe you're doing the same thing more than once, unnecessarily. And you might think, dead code or unused libraries, like, does this really impact performance? Maybe it doesn't have a huge impact on the runtime performance, but it will affect things like your build time and your deploy time. Because if you're pulling down libraries, say via Composer, that you're not using, then A, you have to wait for them to be downloaded regardless, so your build time is slower. Your deploy time might be slower. And also, you're then loading that into memory. So if you're never using that code, you're just wasting memory. So then we all do what every good developer does. We go to the internet and we start Googling around. And there is some sane advice on the internet. Things like don't evaluate your condition inside the loop. Do it once, save it in a variable, use that in the condition. That's fine. Avoid doing database queries inside a for loop. Like if you can do an aggregate query instead of 100 individual queries, that's probably better. That sounds sensible. But then you get things like use empty instead of count equals 0. Or you should use the triple equal operator instead of string compare for comparing strings, because it's faster. And then my absolute favorite, you should use single quotes when concatenating, not double quotes. You should use for each, not array walk, because array walk is a function where you just pass it in an array and you pass in a function as a callback, and then it will execute that callback function for every element in the array. So some people will tell you don't use that because that's an extra call to a function, whereas if you use a for loop, then that's just native PHP, so you don't do that extra call, so it's faster. But then it sacrifices readability. Probably reading through the code, if you see array walk, you understand much better what the code is doing, rather than just looking at a bare bones for loop or for each loop and then trying to work out why are we looping through this and what are we trying to do. And then some people will tell you use regex for some crazy string manipulation because it's faster than the native functions. But then some people will tell you not to use regex because the native string functions are faster. So you're like, where is the truth? And then actually coming back to the list of issues that you have or you might be dealing with, none of those tips on the internet actually help you deal with any of these issues. What do they all have in common? They're all micro-optimizations. I'm not saying they're things we should ignore, but 99% of the time, ignore them every time. Sometimes a lot of those optimizations together can make a difference, even if on their own they will seem very insignificant or there will be almost no difference. Maybe the aggregate difference will actually be something. Especially if you're optimizing a very critical path in your code, maybe they are worth it. But usually they're not worth spending time on unless you can actually prove that this is your real bottleneck. And very often it's not. So you should always benchmark and measure to prove the gains and actually justify refactoring the entire code base to change the double quotes to single quotes or the other way around. And most importantly, just don't avoid fixing the real bottleneck and waste time on these things. So just to show you some stats, these are taken from Tiemo Matig's online PHP benchmarks website. He basically just runs a website where he does online benchmarking of the different functions. So here's the single and double quote myth. Like the top two rows, you're only saving about 4 milliseconds. Like that's a drop in the ocean in the bottom two rows. The variable and constant, either side of the equal sign, which one goes first? Is it one faster than the other? No difference. Preg replace, only 3 milliseconds slower than string replace. That's a drop in the ocean. All right, so if not micro-optimizations, then how do we identify the real problems? Well, the how is actually what most people get stuck on. The general answer is, of course, measure, but then how do you measure, and what do you measure, and how often do you measure? So I was there myself, and I thought it would be useful to do a little demo, like a fake demo, because it's all of screenshots, but basically a walkthrough of how you might actually go about this. Let's start with the tools. It's potentially the first confusing or overwhelming things when you're starting out, because there is a lot of them. They all do slightly different things, and I've kind of grouped them here based on roughly what they allow you to do. So at the top, we've got the general monitoring tools. And they are just for keeping an eye on things or alerting you when things have changed. So they will give you things like your logs, your request times, your CPU usage over time, your app time, and so on and so forth. And they will give you the bigger picture about your application. And you might be able to tell from those graphs if there is anything that you need to worry about. Like if you see the spike in memory or the memory going up, that might be a hint. But they won't really tell you what's going on inside the app. So then the next group is tools which help you simulate the load if you have no production data available or if you're not profiling on production. So there are the load testing and benchmarking tools, and there is a whole load of them. There is one for every language under the sun, and some of them are super simple, some of them are super complicated. Some of them will literally just loop around and do 10,000 requests to the given URL. Some of them, like Gatling and Taurus, they're a lot more complicated. They will allow you to vary the load, specify different parameters. They won't just do the request one by one. They will simulate the real-life traffic and like spikes in traffic and so on and so forth. Even a simple bash loop or like a curl call in a loop, that is a very quick and dirty way of generating load. So use whatever you want to just avoid sitting there and refreshing your page manually. Like, there's no need for that. You can easily automate this. My personal favorite from this is the Go Work tool. It's just a very simple Go app that you just give it a URL and then specify some params. So those monitoring and benchmarking tools will give you the higher level idea. But to have a look inside your app and actually work out what's going on under the hood, you need to dig deeper. So for that, you need more detailed information. You need things like stack traces and call graphs and memory. You want to see what's in your memory at any given time. You want to see the execution times for specific portions of your code. So for that, you need a profiler. And then usually you need a visualization tool on top of that, because the output of a profiler is just random string of nonsense that is not really human friendly. So you usually need some visualization help. So there are a few off-the-shelf really good solutions available, like all-round solutions. Blackfire is probably the most well-known ones, Datadog, New Relic. They all do a great job at giving you your performance metrics, your graphs. They will alert you if something changes out of the box. The setup is usually minimal. You just usually install an extension. You have some daemon running in the background collecting the data. And I'm totally not against them, but I'm not going to focus on those in this talk, because sometimes you can't use them. And I was there myself. For starters, they are all paid. So if your company is not willing to pay for them, you're kind of stuck. And what if you want to profile locally? Like, what if you don't want to send your data to a third party? And sometimes companies are limited in terms of where they want to send the data to. So sometimes you might want to just limit it to your local server or your own infrastructure. But the good news is that there are tools that you can set up locally and kind of achieve the same effect. So this is what I'm going to walk you through today. So how does the tooling landscape look in PHP? Well, to start with, none of the tools are built into the language itself, which is why I put a little Gopher logo at the top, because with Golang, for example, you get all the tools coming with the language itself. With PHP, you have to install them separately, but that's not the end of the world, because they're usually pretty easy to install, usually via package managers. You could roll your own, like the simplest, quick and dirty benchmarking you can do. You can just capture the start time, the end time, subtract the two, and you roughly get an idea for how long something took. But that obviously doesn't scale very well. It doesn't give you the data over time, doesn't let you aggregate. So this is really just a quick and dirty option. So a quick recap just on the slides for how you install extensions in PHP for all the tools. My favorite one is just to use a package manager if you can, so like Brew or apt-get or whatever your flavor is. And that's most of the time you can get away with just doing that. If not, I've posted the slides online already, so this is just a cheat sheet that you can come back to later. And there's always a README in all the projects, so always check that first anyway. So now that we know how to install extensions, let's get ourselves a profiler. And then we have a few choices here. So the two go-to ones in PHP are usually Xdebug and XHProf. And you might be wondering what the difference is or which one do you pick these days. They're both installed as PHP extensions, so there's no difference in how you set them up. I think the history of both extensions explains the difference, and it might help you guide for which one to choose. In the old days of PHP 5, Xdebug didn't have the memory profiling built into it. It just had the debugging side of it. So if you would use that for debugging, but if you wanted memory profiling, you would use XHProf. But then since PHP 7, Facebook stopped maintaining XHProf because they switched to HHVM. And then there were a few people who picked this up and transformed the original XHProf or upgraded it from 5 to 7. So I've put links to three ports of XHProf here. One of them is optimized slightly for PHP 7 with a slightly easier setup. One of them, the Tideways ones, the UI is completely different, and they've modernized the original UI. The third one, I think, is just the original port as it was. But then also Xdebug, since version, I think, 2.6, and also on PHP 7, now has the memory profiling built into it. So now you can use Xdebug for all your profiling needs in theory, except for if you want to profile on production, because Xdebug will make your app 100 times slower, so you should never use that in production. You should always look for something else. And XHProf used to be the go-to tool if you wanted to profile on production, and sometimes you might have to. There is a new kid in town called PHP Spy, and that is a product from Etsy. It was released, I think, April this year, so it's very, very new. It's still very much in like alpha or beta. It only runs on Linux. The setup is very like raw, and you might have to like do some magic there. But it has a lot of promises, because it promises to have such a small footprint that you can run it in production. And it kind of promises to be the Xdebug, but good for production. And it also can produce flame graphs, which is really cool. And it's very exciting because until now, there isn't really an easy way to do that in PHP. And I'll talk about flame graphs at the end. And then I've also put PHP meminfo, and that's an extension for basically taking a look at what's inside your memory when you're running your application. All right, so to work out what your diagnosis is, you need to do some diagnostics. And guessing definitely isn't enough. So I tried to find more of a real-life example of an app that I could go and optimize, because I didn't want to use foods and bars, because that's not what real life is like, and everyone can optimize a simple foods and bars application. So a while ago, a friend of mine, Matt Brunt, he tweeted about his side project called Cigar. And it turned out to be this lovely app written in PHP 7, and it's basically a smoke testing tool. So what it does is it takes an input file, like you provided a file with a list of URLs, and then it will take every one of those URLs, query it, and then you also say what HTTP status code you expect back for a given URL. So you basically call those URLs and compare the actual results, like the actual HTTP code, with what you were expecting. And if something doesn't match, it will then flag it to you. So it's just a very simple tool, takes an input file, goes off to the internet. And I'm kind of deliberately just leaving it at that, because very often that's what real life is like. You're basically just told roughly what something does, but you don't know the details under the hood. And you might not necessarily need to know all the details right now. So imagine a first scenario. The application is suddenly running slowly. Like somebody comes over to you and says, hey, we used to run Cigar in under 1 second. Now it suddenly takes 3 seconds. What's going on? And then your job now is to figure out why. So first things first, and this is something that a lot of people, it's so easy to forget, and I've done it so many times, you need to capture the baseline, because you need to compare the end result against your first initial state to actually know if you've made things better or worse. So don't forget to capture the baseline and the current state of things. So let's set up XHProf. This is how you set it up. You don't have to worry about the code bits, because it's all in the README. You basically paste a bit of text at the beginning, and at the end, you can use PHP directives from prepending and appending this to the files. You can use include files, or you can just copy and paste it between sort of on the edges of the code you want to profile. And then you view the results of XHProf in a browser. So you need to have a web server set up, and then you point the document root at the XHProf HTML output, and then you just see something like this in the browser. And so we can see some suspects already. We have this parse class, and then it calls something called getURLObjects, and then that calls a closure, and that seems to be close to the top. So that seems to be taking the longest. So then what you can do is you can click on the call graph link, and you can view the call graph. And it looks like something like this. So XHProf is trying to be helpful, and it's trying to show you the hot path of your code. And we can see that it finishes on the closure, but then you can't really tell from this graph what's inside it. What is it about this closure that makes it so bad? But at least this gives you an idea of which area of the code to look into. So how do you find out what's going on? Well, we could obviously go and look at the source code, and then maybe we'll work this out. But let's actually use Xdebug for that. So to set up Xdebug, you mostly just have to set up a few PHP init directives. Again, this is all on the Xdebug setup, so you don't have to worry about this. And then we also want to install the visualization tool, because Xdebug will just output a bunch of files that are not really easily understandable. So I like to use QCacheGrind for Mac. I think it's called KCacheGrind for Linux. And this tool is very old. It looks like it's from 1995, but it's actually the most powerful tool that I found still for viewing the profiling data. So we run Cigar with Xdebug enabled. So Xdebug will run in the background. And the output of Xdebug is saved as the CacheGrind files. So then we click to open up the file, and then we get something like this. So it looks pretty old, but it's actually pretty powerful. So I'll zoom into the different areas of the tool in the next few slides. So at the top, you have a drop-down for time or memory. So let's select time to start with. And it basically just lists the functions executed in order of which one took the longest. So you can see that array map is close to the top. And so that we're already sort of at the very low level of your PHP code. And then we also see the familiar parser class as well. So then we can look on the right-hand side. You've got something called the Kali map. And that is essentially a pyramid graph. The first time I saw this, I was like, how do I read this? And I thought you should focus on the areas which have lots of small squares stacked on top of each other, because that's clearly the busiest part of the program. It's actually the opposite. What you look for in this graph is the big empty squares and spaces, because that means that proportionally, that big, fat green square was what took the longest. So lots of little squares doesn't necessarily mean busy. And then if you hover over the green box and I zoom in, then you see the parser class. Xdebug and QCacheGrind also gives you the call graph. So it looks a bit different, but it's essentially the same thing. So it's saying the same thing as XHProf, that the closure is taking a long time. And then debugging closures can be especially tricky because you don't get a function name. Like a closure is a nameless function. So that's where it gets tricky, especially if you have a few closures in your code, and it might be hard to narrow down which one exactly are we talking about here. If we compare the two trees, they look the same. There are two separate runs, so that's why the timings, the data vary slightly. It's like 79% for parse compared to 81. And that's something to keep in mind as well, that because every single run is going to give you slightly different data, usually you just tend to average those out. So if you get slight differences like this, usually it's fine to ignore. So then we can select array map in QCacheGrind at the top, and then we can view the list of the callees, and there is our closure again. And then the cool thing about QCacheGrind is you can jump into the source code right away, so you don't actually have to switch. And it looks like there's some weird stuff in this array map function. It looks like maybe somebody put in some code to calculate pi in a very inefficient way to make this run for 3 seconds. So I put that in the getURL objects functions just for the demo purposes. It's not in the original code from Brunty. So yeah, we removed that code, and then ta-da, we improved things as expected. And always remember to compare against the baseline, against what you had at first, because that's actually your proof. So now when you're sending a pull request to somebody with this fix, you can say, hey, look at the data. Like, I'm proving to you that this is the right thing to do. And then your code reviewer, code reviewing person doesn't have to wonder if this is actually the right thing to do or not. And then after removing this, if you run XHProf, then parse doesn't even show up on the new call graph. And now we have a new hot path indicated. And then if you zoom into that one, it seems to be mostly Guzzle stuff. And that's not necessarily alarming, because you know from what I told you that this app is mostly making calls to the URLs. So now if we see that Guzzle is proportionally taking the longest, that kind of makes sense. So that's not really suspicious anymore. However, it's important to keep in mind to never ignore the library codes. Like, just because this is Guzzle and you haven't written this, somebody else has written this, and it's used by millions on the internet, it doesn't mean it doesn't have memory leaks inside. And it happened to me when we used one of the metrics libraries. And the metrics library, which was used all over the place, had actually a memory leak. So just because something is a third-party code or a framework code, it doesn't mean that it's without any problems. So if you see something popping up in your hot path, even if it's a third-party code, don't necessarily ignore it. So that was a good first step. We made things better. What more can you get from Xdebug, from the output, and from QCacheGrind? Well, you can see how many times every function was called throughout the lifecycle of your application. And you can click around to see what called it. So for example, here I've selected string to lower, and it was called 123 times overall. So you might be wondering, why are we calling this 123 times? Well, you can click on the callers, and you can see that Guzzle seems to be using it a lot in calls to do with request headers. So you're probably thinking it's probably lowering all the headers for comparison or something. So this sort of exploration gives you a really good idea for what the code actually does really under the hood. What else? Well, we see fopen, 9 calls. Well, I've told you about one call to it, one expected call, which would be to open the input file to read the list of URLs. So where are the other 8 coming from? Well, it looks like maybe Guzzle is saving some temporary files, because again, if you click on the list of callers, we can see 1 at the bottom from our parse class. But then the top 2 is Guzzle stuff again. So you might be guessing, well, maybe it's like saving some temporary files. And again, if you click on the source code, yep, that's exactly it. It's saving into the //temp location. So you can really dig down into what the app is doing, even the third-party libraries, to get a good understanding of what's going on. So let's flip the drop-down to memory at the top, and let's come back to the get file contents function. So we saw that it uses fopen. And I've pasted the original bit of code on the left. So if you click on the callers of fopen, you can see the get file open function, and it calls 3 things: fread, fopen, and file size. So it seems like it's taking quite a bit of memory per call, like over 8,500 bytes. So I'm wondering, or you might be wondering, if you know you're always only reading from those files, like they're kind of read-only, the input file is read-only, would it be better to use the file get contents function? And would that be quicker? And sure enough, if you profile this again with Xdebug, just changing the function, it uses less memory. It uses 496 bytes instead of 600. So obviously, this is a very silly micro-optimization here, but I just wanted to show you, like, if you're ever wondering if this function or this way of doing things is better than that way, then this is a really great way to prove or disprove your theory and also get a very quick feedback loop, because all you have to do is just edit the code, run your application again. Xdebug is just running in the background, outputs a new file, you open the new file in QCacheGrind, and you've got the new data. So it's a really quick, easy feedback loop. You don't have to wait for something to deploy, and so on and so forth. So what if you want to do some general exploration? Like, how do you check if your program is not leaking memory? It would be nice to be able to see into the memory and see what's in there at the end of the run. So for that, I tend to use the PHP meminfo extension. It's fairly simple to use. You just add 1 line at the end of the file at the point at which you want to stop and save the memory data. And it actually saves data as JSON files, so they're a bit more understandable. And PHP meminfo comes with a very useful analyzer command. It's a command line tool. You can start with the summary command, and it's very, very useful for just spotting at a glance any objects that you wouldn't expect to be in your memory at the end of a run or at the end of the profiling. And it gives you an exact count of instances as well, so you can see exactly how many objects of every type are there. If there was a memory leak in this case, you just see loads of instances of classes that you wouldn't expect to be there, or like a suspiciously high number. It's really hard to reproduce a memory leak in PHP 7. I tried all the usual tricks for like making circular references to objects to make them stay in memory, or having open file handlers or open buffers. None of this works. PHP 7 is actually really clever at working out what you're trying to do and stopping you. So let's just, for the sake of the demonstration, let's have a look at what we have in this list. And there's our favorite parser class again. So let's have a look at the source code. And this is the main cigar file. So this is the entry file into the application. So it's procedural. We're not into the OO land yet. And this is where we create the parser object to then kick it off. So it looks like we're creating a variable called parser, and then it seems to be staying with us until the end of the execution, like it's in the list, and there is one instance of it. So you might be wondering, why is it still there? Like we know we create it once, we only use it to read the file, and then we never touch it again. So you'd expect the garbage collection to probably just clean it up, because it's never referenced afterwards. Well, let's find out. So you can use the query command with the analyzer tool, and you can filter by class. So if we filter by the parser class, it will tell you things like what's the memory ID of the object, and then it tells us that the execution frame is global. So that makes sense because we're in the entry procedural file, so we're in the global space. It's the root object, it's not a child object, and it seems to have two object handles, like two references. So let's dig deeper and find out what those references to this object are. And to do that, you can use the refpath command, and you give it the memory ID of the object. And then it tries to produce you like a pretty print of all the references. So here we have the two references. One of them is from the global context, and that makes sense. And one of them is the self-reference, which every object in PHP has. So every object will reference itself. So that explains why the garbage collector might not necessarily want to touch this variable. Because it's referenced by the global space, and because PHP is in interpreted language, you don't compile it up front. You have, like, the PHP interpreter doesn't have any idea whether the parser object will or will not be referenced later. Like, it just looks at the code as it goes along, roughly speaking. So because it's referenced by the global space, it's probably just too scared to touch it and leaves it in there. It could also be that this app runs so fast that it just doesn't get to it because there's no need to be particularly worried about cleaning memory. Like, it's not a particularly memory-heavy application. But in theory, this would be like the academic explanations for why it might not be removed. If you had a lot of objects which were referenced by the global scope or in general, then that could then result in a memory leak, because those objects would never be cleaned and they would just stay in memory forever. They could grow over time. So that's something to watch out for. Out of curiosity, I've looked up the globals ID as well, just to see what's in there. And you can see all the familiar things, like underscore post and underscore get. So it's all there in memory. You can all see it. You can get the IDs of those things and then query those. So you can really see what objects are there in your memory, which I thought was really cool for like a teeny tiny extension. So can we make that parser object go away somehow? We know we don't really need it once we're done reading the config file. So can we somehow make it go away? Well, we can use this little trick. We can access the member of the newly created object in just one expression just by doing this and actually avoiding assigning it to a variable. So if we do that, and then we rerun the application with PHP meminfo in the background, then there is no parser object at the end. So again, this is a handy trick to remember. If you're creating lots of objects in the global scope and you know that they're not going to be used, it's basically a hint to the interpreter to, like, don't worry about this object, don't even assign it. So that's a potentially useful little trick. And again, we've got proof. We're not just guessing that this is better than the other way. Like, we actually have the data now to prove it, that this is better because it removes that from memory. All right, so before we wrap up, let's look at another tool which might help you work out what's going on inside your application and where most of your time is spent. And these are called flame graphs. There are a few ways to generate them in PHP. Some of them are less painful than others. It's not super painless. You can use, well, once PHP Spy is more widespread and more stable, you can use that to generate them. For now, I prefer the other alternative, which is use XHProf to generate, to run it with the samples enabled. And then you get that output, you put it through a script, which I've linked to here. That translates it into the flame graph speak. And then you take the flame graph speak and you pass it through Brendan Gregg's Perl script, which then generates the flame graph. And Brendan Gregg is the original author. He invented the flame graphs. So flame graphs looks like they look like this. You get something like this, and you're probably wondering, like a lot of people are wondering, how do I read these? Like, how do I understand these? So if you imagine that thing cut in half, that's exactly what I did here to zoom in a little bit. And a lot of people just are not sure how to interpret this. And they immediately jump to the conclusion that it tells you about time, and it's completely not that. So how do you understand them? I thought I'll try and explain it by using an example of describing to you how I go about my day. So if I was to describe to you what do I do during my day, I might be, well, I'll get up, I'll wake up, I'll shower, I'll get dressed, then I go to work. Sometimes I might take our office dog Bingo for a walk, and then in the evening I might run, I might watch some TV, or I might go and see some friends. And then when I wind down, sometimes I go straight to sleep, sometimes I read books before I go to sleep. So if you were to present this in a graph somehow to work out what I most often find doing, or maybe if there's anything that I do too much of and I should do a bit less of that, how would you present this? Well, if you imagine I had a profiler following me during my day, and every minute it would take a snapshot of what I'm doing, then I would essentially get stack traces of my day. And a stack trace is essentially a chain of functions from the start of the execution, going through all the functions that have been called so far, and ending with the function which is currently running on the CPU. And sort of it was what the profiler found on the CPU when it took a snapshot. So if you can imagine that I would end up with hundreds, potentially hundreds or thousands of those stack traces at the end of my day. Like if the profiler is running every minute and I take a shower for 15 minutes, I'll get 15 identical stack traces, finishing with the shower. So quite a lot of them will be very similar. So if you imagine having thousands of these, how do you group them together? It would be very useful to group them together and identify the common ones, but you're obviously not going to do it by hand. And that's essentially why Brendan Gregg invented flame graphs. He ended up having thousands and thousands of stack traces from a MySQL database application, and he just looked at them and went, how do I make sense out of this? And then he invented these. So the flame graph generation algorithm essentially does this for us. Like it takes all the stack traces and groups the same ones together and figures out the common paths, and then it also figures out where things branch off into different functions. So it produces something like this. It basically just dedupes all the stack traces by keeping in mind how many of each were there overall. So again, you get something like this. If I cut this in half and I zoom in, I get this. Side note, you can use emoji for PHP function names. This is really cool. So these graphs are interactive. You can click about on the diagram and you can highlight things. So you can select just parts of the graph. You can zoom in. There's also a search bar, so you can search for a specific function. Let's just flip over to actual function names, because the emoji are a bit confusing. So the first thing that you might notice is that the functions in every row are listed alphabetically, from left to right. You read this graph bottom up. You can also reverse the graph to get the icicles, and then you would read it top to bottom. But the traditional one, you just read it bottom up. So here in the top left, I have my day, and then I might enjoy my evening, and so on and so forth, like if you read upwards. And then at the bottom, in the bottom half of it, you can see that, again, I start with main, I start the day, I get ready, and then that calls gets dressed, and then that calls something called faff about, that I might not even know that that was there, but that's what the profiler found. So that's how the flame graphs kind of aid your exploration, because you might be sort of spotting functions that you didn't even realize were called. And then I have an overall percentage of how much like faff about was, how often it was found, and it was 14%. So based on that, I could say, well, 14% of my day I spent faffing about. So it really lets you see easily the upstream and downstream functions and like the dependencies between functions. The sleeps at the top, I actually had to make this program sleep to get the profiling data, otherwise it was just running through it too fast and the graph was flat or very unreadable. So the sleeps at the top are it's just the native sleep function. And then a couple of points. The x-axis is it has nothing to do with time. A lot of people assume that you read it from like the start is on the left and you progress to the right. It has nothing to do with time. They're all rearranged alphabetically. So enjoy evening is before, I think, get ready. So E is before G, left to right. So this graph is more for just working out percentage-wise or proportionally how long something took compared to something else. And the y-axis is the depth of the stack. And again, just the fact that the stack is deep it's just like with the pyramid graphs. It doesn't necessarily mean that it's a bad thing or that it took a long time. It's just that there were a lot of nested calls, but they all could have been really, really quick. So the depth of the stack, again, has nothing to do with time. And the colors, they don't mean anything either. A lot of people think that the red boxes are the bad boxes. It's just a completely random choice of colors. He just went for the warm tones palette. And the flame graph algorithm, the only thing it will try to do about the colors is to make sure that no two adjacent boxes will have the same color. So it's just using that algorithm to work out how many colors of a certain palette I need to make every adjacent box have different colors. You can switch this to cold colors if you prefer. So again, red boxes do not mean anything. So this example is a little bit artificial and it's a little bit simplified. Normally this would be a lot more varied, and a real-life example looks more like this. Again, like I said, in the browser, it's all interactive, so you can click on every box, you can zoom in. This, I think, shows the actual MySQL application with all the functions that MySQL calls. Sometimes you have operating system functions show up there as well, but there is a search box, so you can just search for your function and start from there. So hopefully, this all seems a little bit less scary now. Performance optimization can be a little bit tedious at times. Sometimes it will take you a few days, but it's very rewarding at the end of the day, especially when you get the results that you wanted. So some key takeaways. For me, when I look at a problem, I like to start with this question, which is, do I really need to do this? It's so easy to forget. Like, it's so easy to just jump right into the optimization part. But sometimes doing something faster is better, but not doing it in the first place is the best optimization you can ever make. So don't optimize prematurely, and think instead, can I simplify this? Can I just get rid of this entirely? So this applies to dead code, operations that you can only do once. Maybe you can save some HTTP calls, anything to just make the code simpler. Simpler code is a lot easier to optimize. Prioritize what to focus on. Look at the gains versus effort, and basically improve the most important things first. Ignore the micro-optimizations for the most part, and remember that the design, like overall design changes to your application, very often will trump the individual code changes that you make. So sometimes you might actually have to take a step back and then just redesign the application, for example, to make it concurrent. The hot paths are usually the things to focus on, but not always. So take it more as a hint, not a given. Customize for the optimization that you're doing for your own needs. Don't be afraid to break the rules if that fits your use case. There might be some unconventional or more unconventional ways of coding something that might actually be faster for you. So it's just like with denormalizing databases. In theory, you should get to the third normal form, but if you're doing a lot of reads and you're just always joining tables, you're probably better off denormalizing this and doing it that way. So just like that with optimization, don't be afraid to break the rules if it works for you. Use the data to prove your guesses, measure everything, but keep in mind to do it with minimal impact on performance, especially if you're doing this on production. And remember that optimizing performance is an iterative process. It's not enough to do it once. You need to know your trends over time. Sometimes things just come out in the wash on production after your application has been used for some time. So you should aim for more just iterating over your solutions over time to adapt it. And whenever you upgrade your infrastructure or your components, you should redo all your performance testing, because things might have changed between versions, things might be now faster or slower. Maybe some of the optimizations or workarounds that you put in before don't apply anymore. Maybe they're not necessary anymore. Like, a lot of things go away when you're upgrading from PHP 5 to 7, for example. Your hardware might have changed, your configuration, how many cores you have, all of that might have changed. So have monitoring in place, however you can make it happen. And try to have some alerting as well based on those trends, so that you don't have to wait for your customers to tell you that something's gone wrong. If you can get to the point of having automated tests, then again, that saves you a lot of manual work, and it will really help you prevent the performance degradation over time. You can even correlate your deployment points with the performance graphs to get like a VIP experience. There's a really good blog post by Etsy on how to do this from a good few years ago, but you essentially get graphs which shows you like after this deploy, say the memory usage started going up. So you know exactly what you've changed and what you might have to roll back. If you have any questions, feel free to tweet me or grab me afterwards. I'll be around and at the social. And thank you for listening.